For Chapter 2, we'll consider Einstein's special relativity when applied to Newton's universal gravitation. However, to understand special relativity, consider the orbit of star S4714 around Sagittarius A star when the Kepler equations are applied. Note, the mass of Sagittarius A star is 1.954 million times the mass of star S4714. Traditional prerequisites for the application of Kepler's laws are the primary mass must be much larger than the secondary mass, and the orbiting object must have cleared its orbit of all other objects. The difference between Kepler and Newton is that the secondary body describes an elliptical orbit around one of the foci by the primary where the primary body sits, while with Newton, the primary and secondary bodies co-orbit about their common barycenter, which sits on the focal point. Since the barycenter of this Sun-Jupiter system is just off the surface of the Sun, an assumption that Jupiter is the limit for the use of Kepler equations can be supported. Since the mass of the Sun is 1,048 times the mass of Jupiter, I'll assign the first Kepler prerequisite as the primary mass must be greater than 1,000 times the secondary mass. Also, since Newton says that every object affects every other object rather than clearing its orbit, I'll state that Kepler is only valid for a two-body system. If there are additional objects cohabiting the orbit of the secondary object, then Kepler cannot be used. For example, the barycenter of the Earth-Moon orbits around the Sun, resulting in both the Earth and the Moon having wobbly orbits. Likewise, while Janus and Epimetheus share a common average orbit, they swap between inner and outer positions whenever they get near each other. Also, if there are additional objects in other orbits, then Kepler equations are valid only for one orbit, because whenever the object orbits underneath another, its eccentricity is changed, altering the orbit. Since Sagittarius A star has a mass of almost 2 million times the star of 4714, it qualifies for the first condition of the Kepler equations without prejudice. While star S4714 personally experienced the Kepler ellipse, an outside observer witnessed a stretched periapsis where the lacus rectum is 190 degrees instead of 180 degrees. The reason for this, according to special relativity, is that the star experiences time dilation according to Lorentz equations. As a star's velocity increases, it experiences time dilation by 0.3% at the periapsis. This decrease in observed velocity from the observer's stationary relative to Sagittarius A star. The textbooks state that the mass of the star increases, which increases the momentum that causes the arc to be stretched, and the textbooks are wrong. The conclusion was reached by applying Descartes' momentum equation of 1644 to Kepler's planetary equations of 1609 and 1621, and taking a shortcut. The experienced momentum is the product of the experienced mass and the experienced velocity. The mass experienced by the star is its rest mass, while the velocity experienced is the change in experienced distance divided by the change in experienced time. The experienced distance is the distance, which is also the observed distance, but this will change in a later video. The experienced time, according to Lorentz, is the observed time divided by the Lorentz factor, lambda. If we multiply momentum by one in the form of lambda over lambda, then the two lambdas in the divisor cancel out, leaving rest mass times Lorentz times change in distance over an observed time. Since the change in distance over change in observed time equals the observed velocity, this leaves rest mass by time dilation equal to observed mass. The term was it is as if the mass was increased. And while there is no actual mass increase, the math works when applied to Kepler, because the source of gravity for Kepler is one of the foci. Time dilation should only be applied to time. While we observe a mass increase, we must recognize that the time dilation observed mass is not rest mass. Increasing mass will not work on the Newtonian equations. The force of A is the product of object A's mass and acceleration, which is also equal to the universal gravitation equation. By canceling out object A's mass from both sides results in object A's acceleration being equal to g mb over d squared. If we increase the mass of A by lambda, the lambda A cancels on both the lambda ma cancels on both sides, resulting in the identical acceleration of object A. This was demonstrated by David Scott in 1971 when he simultaneously dropped a feather and a hammer while on the surface of the moon. Since the hammer weighs 10,000 times that of the feather, if Aristotle was correct, the heavier hammer would fall faster than the lighter feather, as we witness on Earth. However, if Kepler and Descartes were correct, that the only source of gravity was the moon, then the feather, with less momentum, would plummet and crash on the lunar surface, while the more massive ham would gently drift like a stone until it settled hard on the lunar surface. As it is, Newton prevailed. Both objects fell at the same rate. This demonstrated that increasing the mass of S4714 around the periapsis would not slow the rate of speed increase, nor increase its time to complete the part of its orbit. It also demonstrates that space-time is not a single fabric, but every object views a different elapsed time with respect to its velocity. If we apply the Sun-Jupiter mass ratio of 1,000 to 1 to Lorentz time dilation, then if time dilation, which is 1 over the square root of 1 minus the velocity over the maximum speed of light squared, is less than 1 plus 1 1,000ths, we obtain a velocity of 4.4% the maximum speed of light. Any velocity of less than 4.4% c results in a time dilation of less than 1.001. This means that time dilation can be ignored, and Newton's equations can be used to approximate the orbits relatively accurately. Also Kepler if the prerequisites are met. Note the velocity of both the lactus rectum descending and ascending points are both below the limit of 4.4% c. The velocity of the apoapsis is about 0.056% c, resulting in a time dilation of 1.00000001585, or less than 5 seconds per Earth year. This means that from the lactus ascending point to the apoapsis, green, to the lactus rectum descending point, orange, time dilation can be ignored, and the Kepler equations prevail. This is because the maximum time dilation, which is at the lactus rectum, is 1,259 to 1, or only about a minute per Earth day. This is how we find other objects orbiting about Sagittarius A star, by the slight variations of known stars like S4714 when compared to the Kepler eclipse. There's another matter near the periapsis. On the velocity of 8% c, we have a time dilation of 307 to 1, or over 4.5 minutes per Earth day. The relatively short distance covered in 4.5 minutes each day at 80% c, when covered to the distance to Sagittarius A star, means that there is a relatively large arc for the short time that the star passes from the lactus rectum descending point through the periapsis, blue, to the lactus rectum ascending point, red. and it changes the angle of the lactis rectum from 180 degrees to 190 degrees, causing a final apoapsis to be 10 degrees further than the initial apoapsis. In the next video, I'll apply special relativity to our ideal scenario.